So what I'm going to be talking about today is using deep learning, in particular RNNs, which we've heard a lot about so far, for real-time anomaly detection. Here's a quick agenda of what we're going to be doing. I want to start off just with talking about the problem landscape, so we have a common language on the sorts of problems that we're actually approaching. We'll go through some traditional strategies, so static anomaly detection, time series anomaly detection, some of the things that were more popular a few years ago before RNNs came into their own. And then we're going to dive into deep learning strategies, talking about time series forecasting with RNNs, how you can use that anomaly detection, and in particular, the fun stuff, which is what are the common issues that you might run into, and how might you address those issues? All right, so starting off with problem landscape. There are some key questions that we all need to understand and make sure that we don't bleed our usage of one of these concepts with the others. So supervised and unsupervised, what is going on with anomaly detection there, in particular in the time series case, multivariate versus univariate, and how you can use multiple input features in your forecasting, and also are you classifying for anomalies with respect to multiple features. And then, of course, using static versus time series data. So for unsupervised and supervised, at a very fundamental level, anomaly detection is an exercise in unsupervised machine learning. What you're mostly trying to do is find those data points that are different in some way or in relevant ways from the core behavior, the core patterns that you tend to see in your data set. However, supervised learning techniques creep in there all the time in all sorts of ways. So specifically for the predict and analyze strategy, where you're doing time series forecasting, and then you do your analysis of the residuals, which we're going to focus a lot of the back end of this talk on. That's going to be an exercise in supervised learning. Also, when you're integrating feedback, which is something that inevitably you're going to want to do for most anomaly detection use cases, that's also going to involve supervised learning. All right, so another important boundary that we're going to want to keep straight in our mind is a multivariate target versus univariate target, and this is different from multivariate input versus univariate input. So here we have a nice diagram that I made with GDocs. And we see you have your x1 feature here and your x2 feature here, and there's a clear relationship with the standard data points, these blue data points. It's roughly inverse linear, and that would be the area of normal behavior. And in that case, this red guy is clearly out of bounds of the normal expected behavior. However, and that's if it's two-dimensional. However, if it's one-dimensional, you might see, if you look at this is going to be the distribution of the data points. The now green guy, this guy that was anomalous when you look at two features simultaneously, the x1 and the x2, now is right in that meaty part of the curve of the distribution. So how you consider your target features is going to have a big influence on what counts as anomalous or non-anomalous, and depending on your use case, it's going to be something you want to pay attention to. All right, the last bit of perfunctories that I want to go over is static data versus time series data. So if you look at the distribution here on the left-hand side, when you have something that's relatively periodic, it's going to be basically a uniform distribution. You have as many data points up here as you do over here if you sort of like project them over to get a distribution right here, right on the left-hand side of the curve. And what that means is that just looking at the distribution is going to be kind of a poor way of detecting when an anomaly happens, because if you break the pattern, as you might break over here in this time series, you're going to end up not seeing it at all. It's squarely in the center of that distribution. So when you're talking about time series data, it's going to be very important to actually not just talk about the distribution of where the data points are, but also where that data points should be at that moment in the time series. All right, now let's talk about some traditional strategies. So the first one that you probably learned when you were in grad school or when you were just Googling scikit-learn or whatever it was, is probably one class SVM, or sometimes called new SVM for the key parameter there. This is the bread and butter. It's highly non-scalable. Usually you use a nonlinear kernel. And what it does is instead of separating the positive and the negative cases, the ones and the zeros, what it's going to do is find a separating hyperplane that separates from the origin, and usually with a nonlinear kernel. And you end up getting a graph like this. This was an example that is pretty easy to pull up using any of the open source implementations. Another traditional tactic is Gaussian mixture models. Gaussian mixture models is an exercise in fitting a Gaussian, usually hopefully a Gaussian with off-diagonal covariance matrix terms. And those off-diagonal covariance matrix terms, or if the diagonals are not identical, are going to end up giving you heat maps that are, well, contour maps that are ellipsoids, and ellipsoids with different shapes, different rotations, and different major and minor axes. These are two-dimensional, but you can imagine with your 6- and 7-dimensional visualization how this can look, what this might look like in more than one dimension. Typically, it's done with expectation maximization, and then you'll loop through k equals 1, k equals 2, k equals 3, and have different metrics for fit to see which is the right number of modes to add. And while there are fewer open source implementations of this, you can also do this with distributions other than Gaussians, which you might very well do in different, depending on your use case. The last one, which is I think probably now a little bit less popular, a little bit less, we might not have seen this before, is the technique for taking a moving window of vectors and then plotting those, creating vectors in a vector space based on that moving window of a select time series. So for visualization purposes, I've chosen a window size of m equals 2, and then you kind of run down there and you plot each of those data points in your space, and you might see a pattern, right? You might see that, oh, most of my curves end up, and if you think about it, each of those windows is going to be a snapshot of a section of a curve that you might see in your time series, and you can get the normal ones, and then you can get ones that may not happen. Now, there are all sorts of famous examples that I don't want to get into on the pros and cons of this technique. The most important thing that you want to make sure that you do here is choosing your window size m is very important. It has to be large enough to capture time series relevant patterns. If you make it too short, you're going to end up seeing basically every kind of shape there is. If you make it too long, you're going to have cursive dimensionalities. So figuring out techniques for managing that, for maybe having a moving window vector embedded, and then doing a kind of encoding like Sachs encoding, which I have in these references at the bottom, that's the way you get around that when you're doing this sort of strategy. All right. Last but not least, and the one that we're going to be focusing the rest of our time on, is the forecast and analyze residuals strategy. Or predict and analyze residual strategy. So this one is hopefully very suggestively described by the diagram. You have your time series. At this time at time t, you predict your next data point, which you expect to be here, but your actual might not be there, and then depending on how much your actual misses your forecasted, you're going to end up, so that is to say how bad your residual is, you're going to either classify it as an anomaly or not an anomaly. This is something that there are lots of different approaches to this. There are lots of different approaches to how you're going to forecast and what you're going to do and what counts as residual scoring the how big of a residual is a detrimental residual, and typically that goes into, again, static distribution analysis. So you might fit it with a GMM, a one-dimensional or n-dimensional GMM, and then you'll find the low probability areas of that residual space. Typically, hopefully, if you built your LSTM right or you built your forecaster right, you're going to end up with something that is unimodal, but there are all sorts of cases where you might actually, depending on the pattern of the data, end up with more than one mode, and you might have to manage those tricky values in the middle. One more moment talking about this. I've talked about a univariate residual. But you can also imagine if you have an array of sensor data and you're tracking several time series at a time, you would have a residual that you might see in each of those sensors or for each of those sensors. So you can do not just univariate residual analysis here for the static case once you create your residual vectors. You can also do multivariate, and so it's very flexible in that way. All right, so last bit of non-deep learning. There are a lot of traditional time series methods out there. There's ARIMA and exponential smoothing, and Gaussian, and generalized autoregressive scoring. Often what you'll run into is low flexibility. They'll have difficulty adapting to certain kinds of patterns. They're more or less designed for detecting very specific kinds of patterns. And so if you have fluctuating phase or things like that, they will or they can tend to break. And just a shout out especially to the forecast package, which is the reason why probably a lot of you still broke out R even in this day and age. Thanks to Rob. And over the summer, Ross Taylor released PyFlux, which is a Python implementation. Okay, so now recurrent neural networks. So these probably don't need an introduction this late in the day, but just in case, we have this sort of structure where you're passing out your output HT, and you're also passing back certain results that happen in that recurrent neural network unit. Excuse me. So what does it look like on the inside? Really quickly, throwing up the LSTM framework there, which is a very common one and actually a pretty good one that we found for anomaly detection. LSTMs, as we saw earlier with the Salesforce presentation, are really good at keeping track of what I should remember and what I should not remember. And so you have your forget gate, your input gate, which are all going to take into account the hidden the hidden features, the X feature for that time point, the hidden features from the last time point that were passed from the last stage, and a learned bias vector. So that's going to affect the output gate, the input gate, and the forget gate. You're also going to have this new X data that's going to throw into a sigmoid function and be taken with a Hadamard product for the input gate. And then that will help you update the state of that cell. And the state of that cell might be wiped away if your forget gate gets triggered. Yeah, and then the equation 5, we see that the output will be a result of the output gate hidden, usually with a tanh. Now, there are all sorts of modifications to LSTMs. I'm only going to go through a few. One that can work out very well is if you give a little bit more control to the cell state with peepholes. So the cell state will actually influence the forget output and input gate, and you'll see that in these purple components of the equations. Another really great advance in LSTM architecture that is a little bit more recent is adding in phase. So this can be very important, especially when you have different sensor arrays, and the different sensor arrays might bring in data at different times. You might get one bit of data with constant telemetry. You might get one that is only going to take a snapshot every 10 minutes or every hour, and they might not come in exactly at the same time, the same phase. So what you end up with is building in these phase gates here and here. So in order to go from the pre-phase cell state to the post-phase cell state, you're going to end up weighting that with an on-off switch, depending on the state of the phase, where it is, and you can control the period of the phase. You can control where the phases are, or what the relative phase is from one to the other, and also the ratio of on and off. In this paper with Neil et al., they experimented primarily with these spikes of just turning on and turning off and having a ratio there. But you can easily imagine doing something that's a little bit more continuous. All right, so RNNs as forecasters are great. So first of all, something that is not easy but can be done with traditional ones is you can incorporate exogenous variables. You don't have to just pull in the last time series point or the last sequence of time series points as you run it through. You can have whole vectors. So even if you want to have a univariate target for one particular feature that you want in a time series, you can pull in the entire vector of, say, sensor data or whatever it is you find is relevant, and that will help you see, for instance, let's say you have a machine and the different machine parts are adjacent to one another, seeing one time series fluctuate in a certain way, or one feature input fluctuate in a certain way might actually have an input for the final output that you care about in the time series that you're looking for anomalies. So looking at that cross influence can be very helpful. You can also use, you can use external context variables. So these are ones that are not going to be necessarily time series, but the status on the ground. So what's the location or the weather, things like that. You can do other sensor data. And something that those of you who have worked in time series field before are going to probably find it familiar that sometimes when you have constant telemetry, you actually don't get that continuous telemetry. What you end up getting is chunked up snapshots, and instead of getting, so like let's say every hour, you might get a snapshot at that hour of the mean, max, min, and standard deviation for what happened in that hour. And so in order to unpack that non-constant telemetry, but pseudo-regular information that you get, you might want to take into account the standard deviation during that period, the max and the min during that period, in order to get a better forecast. All right. Now for the exciting stuff. How do you, what actually goes wrong when you're building these, and how do you fix it? So there are several topics I want to go over. Truncated backprop, so how big your lookback should be, avoiding blowups in your gradients or vanishing in your gradients, and also just making sure that you have the right look back in the time series relevant for forecasting. Stacking, dropout and regularization, so controlling for that overfitting. What kind of optimization method you care about, what kind of error metrics you care about, and also smoothing techniques. So for stacking, I was describing in that original diagram just that first layer, but it's not hard to see how you can take the output of a lower layer and feed that into a next layer, and you can really make these arbitrarily high. LSTMs are actually fairly good at stacking, and so you can add more degrees of freedom, you can add more flexibility, and a greater ability for your time series forecaster to detect the relevant patterns and get the more accurate next result if you stack. That's the sort of thing that you're going to hypertune. Now, when you're adding these degrees of freedom, you're going to want to also make sure you're not overfitting. Dropout is this is something that we should all put in your heads and remember as a thorn. Dropout doesn't work for horizontal arrows in LSTMs. It can corrupt really important information that happens early in the time series that should pass through. What dropout is, for those of us who haven't worked on it or worked with it as much, in dense networks it turns out to be very well. What you do is you want to prevent overfitting, where one part of a deep net might learn one pattern, but it's also kind of drifting towards a certain kind of weight structure, and then another part of the network will actually compensate for that. So if you have enough parameters, if you have a big enough network, you'll end up sort of compensating with the parameters over here, using the parameters over there, and it'll end up being accurate and balanced, but it's inefficient and it's not going to be as stable. And so what dropout will do is kick out randomly different edges and see if and then continue to train the matrix what happens when it's only got 2 legs and 1 leg instead of 4 legs. And that can be very effective when you're not talking about LSTMs. When you're talking about LSTMs, because that time series pattern is very important, doing for the horizontal arrows, dropout is not suggested. Instead, you might want to use regularization for those horizontal arrows. You can still use dropout for the vertical arrows. Okay, so one of those good problems, because LSTMs are so good at doing time series forecasting, they might actually adapt to anomalous periods too well. So you might actually get into the stage where you have a period of normal functioning, then something happens, and now there is a period of non-normal functioning, but your forecast curve can actually adapt and start forecasting the anomalous behavior very well. And that's going to be a problem if you are in the business of detecting anomalies. You kind of like forecast the new normal, which is a phrase we hear a lot nowadays. Lots of solutions you can have for this. One that's relatively intuitive is you could change your error metric. So if you're starting with mean-squared error, that's going to weight the big outliers a little bit more. So if you roll it back to an AE or a log loss, you're going to give less penalty to those big differences, and that could help with that quick adjustment to a new normal, to a different kind of time series. Often that does not work well on its own. You might also try this in combination with other techniques, for instance, multiple predictors. So multiple predictors, you can imagine I've been focusing on predicting at one time step back, but you can do it at several time steps back. And what that's going to end up doing is it's sort of like a moving average of the forecast. So your actual forecasted term is going to be what was forecasted one time step back and what was forecasted 2 time steps back, where it forecasts, and then it forecasts on the new time series, and 3 time steps back. And that will end up pinning the behavior that happens back here as more of the normal kind of behavior, and that'll hopefully prevent that over-quick adapting to a new behavior. Of course, something that should be obvious, but it's worth mentioning, if you have known anomalies, retraining with those anomalies redacted will help you identify the normal behavior better. You don't want to learn on the anomalies if you can help it. And then the last one, which I'm going to take a couple moments on, is the encoder-decoder architecture. So what is that? Going back to this stacked LSTM picture, you can see how a sequence of your time series has lots of different paths for getting to this final stage. So it can go through, like, information travels through each one of these edges. And one of the things you could do is actually, much like you see for autoencoders with dense neural nets, you can also have this encoder-decoder structure for LSTMs. And what you end up doing is you have your input sequence, you feed it through, and then you get your output sequence and try to reconstruct that data. And why do we care about that? Well, the whole idea about fitting it through this keyhole for the encoder-decoder is that the normal data, the normal times of time series that your LSTM network is training on will learn to adapt and to let those things fit through the keyhole. The keyhole will kind of adapt to what's normal data. And then when you see abnormal data, when you have abnormal time series, then those are not going to fit through that key very, very well, and they might have poor reconstruction. All right, so this is the same graph, and that's suggestive. It might not be that you are adapting too quickly to a new normal. It might be that this is actually the pattern that is expected. So you might think it's maybe a phase function or something like that. And if you have different kinds of data, might have a natural daytime-nighttime behavior, and it might be discrete. It might be more gradual. But if there's a sudden change, let's say 8 o'clock, the lights turn off, and the entire system powers down, you might end up getting a one time step or a couple time step spike. So you get this spike in the residuals, and that spike in the residuals is really just an artifact. It's supposed to shut down there, and that's sort of a sudden change. So in a way, it's anomalous, but you don't want your LSTM to detect it as anomalous, because this is going to happen every day. And so you'll tend to see the same kind of spike. And how do you manage those spikes? This is going to be dependent on the kind of data that you're working with. Well, you can do smoothing. You can do moving average, which is what we have here, but you can also do exponential smoothing. You can do autoregression. So all of the kinds of smoothing that work with traditional time series can also be put as a layer over your residuals, and then that'll make the residual analysis that much easier. All right, so couple more thoughts on how you do integrating labels. Some examples of this in action with a little bit of demo, and then we can get into questions. So how do you do integrating labels? Well, number one, there are going to be certain kind of outlier behaviors that are not true anomalies. At least they're not the sort of thing that with your data you want to get alerted to all the time. And so you might want to build a classifier supervised learning, where you get feedback from an SME or from somebody who's actually in the position to review the anomalies that you're going to release as part of your algorithm, and give some feedback on it. So circle the good ones, X the bad ones, and then you could just build a natural classifier to filter out the false positives, the false positive anomalies. This can be done in all sorts of ways. You can use your own classifier. You can actually do an LSTM for that, so you use all the exogenous variables. But that sort of structure is very similar if you want to go the LSTM route, as I just described, only now you're forecasting your HT, so to speak, is not the next time point. It's going to be a prediction of whether this is going to be a genuine anomaly or a non-genuine anomaly if it comes out that way, if it's flagged as an anomaly. Improved tuning for residual analysis. So we talked about smoothing. We talked about doing residual analysis when you have, how big of your, how far out in your tails or in your distribution, low distribution values, what counts as a true outlier in your residuals. And so getting that feedback will help you. You can integrate that in a very natural way in order to tune where you're going to set your threshold. And then retraining. So again, these algorithms work much better when you can pull out the anomalous periods as much as possible. So after you get the confirmed true positive anomalies, you might want to kick those out of your time series and retrain, and then your forecaster will be that much better. All right. So here is an example in action. And maybe we can just do questions while this is running. This is kind of a drag and drop demo of a tool like Corvana that does precisely these sorts of things in the background. I'll stop it when it gets a little bit later in the video to talk about how this is integrated. But I think since we've got only 5 minutes, maybe we should start with questions.
All right, so if you have questions, please raise your hand. I'll bring the microphone to you.
With ARIMA models before, I found that the choice of the parameters as well as your choice of exogenous variables could really shift the residual profile. And I'm wondering if you found the same thing for your models, like finding completely changes, like what are large residuals, what data points are small residuals.
So so what you're saying is that when you do like an ARIMA X, depending on what those X's are, that can really impact your residual analysis. Exactly. Yeah, certainly. The residual analysis does need to happen. You need to do a separate residual analysis for every LSTM model that's going to, and just like for any ARIMA model or other kind of model like that, because you're going to have quite a different residual behavior. Depending on your forecasting. We see here, this is one of the parts, getting the feedback is important. You can see that you actually will, if you can create that blue cloud of confidence intervals and p-values, so how bad of a residual is a bad residual, you can end up flagging the ones that are outside of there. And then here we have an example where you have several different metrics coming in simultaneously. So not only are they all cross-pollinating, influencing the forecasting for one another, they also can be analyzed independently and actually in a multivariate static, multivariate residual analysis as well.
Yeah, my question is, for the univariate single time series case, how much data do you actually need for these deep learning models to work?
Totally depends on the data. With time series, with telemetry, it's one of those situations where because you might have one sensor, but because you're constantly getting in new data, unless it's like once a day, usually the volume of data is not as big of a problem because after, if you're getting like once a minute or once every 10 minutes throughout the day, it's not too long before you start building up millions of data points.
What about like once a day? Or much more sparse metrics. Have you worked with those and seen those in practice?
Once a day is probably going to be rougher unless you have several years of data. So a few thousand data points, then you might want to shift more into short-term, low-train examples. And the Numenta data set is probably a good example of that genre of anomaly detection.
Any more questions?
Hi, so if you have different variables, are you going to build different multiple LSTM models for each variable, or same LSTM model can scale to multivariate?
Yeah, that's a great question, an important one to get straight. You would feed in potentially all of those variables into your LSTM model, but then you would have a different LSTM model, each one of which is responsible for predicting the next time point for that particular metric. And then you would get your residual for that particular metric for each one of your models. And then you would do residual analysis. Another alternative is you could do a forecasting. Remember, LSTMs can forecast on multiple dimensions. So you can also have it be multivariate in and multivariate out. This is something that's harder to do with like ARIMA X. And then you could do your multivariate residual analysis or your univariate residual analysis on the differences for each one of those features.
Any more questions? Please raise your hands. Thank you very much.
Thank you.